welcome to another fantabulous Java programming lecture on the Euclidean algorithm with me, Professor Mimi Rasky. This is going to be a fun time today, so I hope that you'll join me in discovering a really cool way to find the greatest common divisor of two integers. So this is a very famous algorithm, and the name of it is called the Euclidean algorithm. Let me see if I can write this okay. So if you're following along with your lecture notes, fill in the blank. So what we're going to do here is we're going to look at some examples of finding the GCD, greatest common divisor, using the algorithm. And as we're doing that, we're going to be referring to sort of a little bit of how we're going to put that into place using Java code. We'll do some pseudocode, and then finally we'll write some actual code for this method that's going to be called Find GCD Faster, that accepts two positive integers for parameters, and it'll return the GCD. So let's talk about sort of the beginning algebra way to find the GCD. So what do we already know? Like the GCD, and this is common notation, to put GCD and then the two numbers inside parentheses. The greatest common divisor of 9 and 3 is 3, because 3 is the biggest number that divides both of those evenly. What is the GCD between, say, 18 and 24? Well, you may be able to do this just by inspection. It is 6. What about the GCD between, say, 10 and 49? Well, those two numbers don't have anything in common except for the number 1. So that would be their GCD. Now, when this happens, we say that these two numbers are relatively prime. So that's kind of important, and that's something in number theory. It's not that those numbers are prime, because both 10 and 49 are factorable by something other than 1 in itself, but with respect to each other, they're relatively prime. Okay, so how do we find the GCD if we were just in an algebra class? Okay, real quick, this is how I do it. Let's just do it for 18 and 24. I prime factor both of the numbers, and that means writing them as a product of primes. 18 is 2 times 3 times 3, and 24, when we prime factor it, it's 2 times 2 times 2 times 3. Then I draw a line, and then I tell my students to look for the matches. Anything in common? Well, they both have a 2 in common, so I write that down. Is there anything else? Sure. They both have a 3 in common, so I write that down. Anything else? Nope. Multiply these two numbers together, and there you have it. You have the GCD. But it does involve factoring. The Euclidean algorithm is great because it involves no factoring at all. So that's the beauty of it, and it's a little bit quicker. So how would we do this very same problem that's kind of easy here using the Euclidean algorithm? So to do this, we first label our initial integers big and small. So I hope that you can appreciate that the 24 is going to be my big and the 18 will be the small. So then what do? Well, the idea is you're going to want to write a sentence here that is going to look like this. Big is equal to small times something, that's a question mark, plus a remainder. And so how do we actually write out that sentence? We're going to do some long division. Sorry, you can do this with your calculator if you like. So how many times does 18 go into 24? Well, only once. And when we subtract 18 from 24, we get 6. So what does this mean? It means that we're able to write this big equals small times something. So 24 is big. That's equal to the smaller of the two numbers, 18, times 1, plus the remainder we got, which is 6. So would you agree that 24 is equal to 18 times 1 plus 6? I hope that you can agree with that. Now the idea here is to pick a new big and a new small. So 18, which used to be the small, is now going to turn into the new big. So he sort of gets a new role here. And the remainder, which was a 6, he's going to take on the role of the new small. So anybody here on the left-hand side is referred to as the big, and then equals small times something, we're going to figure that out in a moment, plus a remainder. Okay, so with this example, I hope you can appreciate that 18, which used to be our small, is going to become the new big, and 6 is going to become the new small. So we're asking how many times does 6 go into 18? And it goes in evenly, 3 times. So that means we have a 0 remainder. So we can write our sentence, 18 is equal to 6 times 3 plus 0. And when the remainder is 0, that's when the algorithm stops. And so that's not the GCD, though. The way the algorithm locates the GCD is at the moment you have a 0 remainder, whoever was the last value that was in the small place is the GCD. So there's sort of the winner there. So that's how the algorithm works. And I'm going to do a much bigger example with some large numbers so you can see this process more than just a couple of steps, because this was kind of an easy example. So I have appended a new page here. So before we do that big example, what if I wanted to see how it would work if we would find the GCD between 10 and, say, 49? How would that work? Well, once again, we locate who's the bigger of the two. They get to be the big, and the other one is small. So if we write big is equal to small times blank for now, plus the remainder blank, how is this going to be? Well, 10 goes into 49 4 times with a remainder of 9. So when I write this sentence out, it's going to go 49 is equal to 10 times 4 plus 9. So then what happens? Well, the 10 gets to be the new big. So he takes on the role of the new big. And the remainder, which is 9, gets to take on the new small. So when we are going to write out the sentence again, 10 is equal to 9 times blank plus remainder blank, we can come over here and do our long division again. Now we're saying 9 goes into our new big, which is 10, how many times? And that's only once, and then we get a remainder of 1. So when we write that out, we're saying 10 is equal to 9 times 1 plus 1. So then what happens? So, remember you've got the new big and the new small. So what do we have? We have the new big is going to be 9, and the remainder is going to be the new small. So 9 is equal to 1 times blank plus blank. Well, 1 goes into 9 how many times? I think that you could see it goes in 9 times exactly with a 0 remainder. So 9 is equal to 1 times 9 plus 0 for the remainder. Remember, that's when you stop. Who was the last guy that was in the small location? It was a 1, and so he's the GCD. So these two numbers that are relatively prime, the Euclidean algorithm works just as well. So let's do a big number and another large number, and that's what we're going to start looking at how Java would code this up. So this is sort of the challenge problem. What would be the GCD between 7,546 and 588? Now, we could factor it, but the algorithm doesn't involve any factoring. So first, let's take a look at who's the big and who's the small. And remember that we want to write down big is equal to small times blank plus blank, the remainder. So if I'm going to do some long division here, 588 goes into 7,546 kids. Okay, 588 goes into 754 once, and then if we take 588 away from 754, we have 166. Bring down the 6. 588 goes into 1,666. Oops, sorry, that's right. It goes in twice. But then that's 2 times 588 is 1,176, And let's see, when we do subtraction, we get 490. So there's the remainder. So when we write out the actual sentence here, we're saying our big number, which is the 7,546, is equal to the small, which is 588, times 12 plus a remainder of 490. Now, I hope you can see that this 490 is actually the modulo when you do 7,546 with 588. So in other words, the remainder is going to be big modulo small. And then this number here, where we got a 12, this number is simply the division, integer division of big divided by small. So there's a little bit of Java coming into the play there. Now what's going to happen? Well, the one guy that used to be small will be the new big, and the remainder will be the new small. So now we're asking this question, how many times does 490 go into 588? And so this is where you kind of keep going with your division, where 490 is the new small, and it goes into 588 how many times? I believe only once. And when you do the subtraction here, you get a remainder of 98. So when we fill in the blanks here, 588 is equal to 490 times 1 plus remainder, which is 98. We're still not done. Remember, it has to have a remainder of 0 to stop. So we keep going. But at this point, I wanted to mention something kind of cool that's important with the Euclidean algorithm. I think it's cool. At this point, what's happening? The GCD of our two original numbers, 7,546 and 588, is now reduced to a little bit of an easier problem, where we're just finding the GCD between the new big and the new small, which is 588. This doesn't let me get too close to the edge here. The GCD of 588 and 490. And that's kind of an interesting fact. So we got to keep going, though. So what happens? 98 is going to become the new small, and 490 is going to become the new big, and we have to fill in these blanks here. And so this is where getting a calculator is maybe useful. It turns out 98 goes into 490 exactly 5 times, and we get that 0 remainder. So that's lovely, and so then the algorithm says stop, and 98 turns out to be the GCD. Okay, so what can we write at this point? We can write that the GCD, we don't get too close to this, GCD of 7,546 and 588 is 98. Nice. Okay, how does this translate into code? So I hope that you can see that if we look at some pseudocode, first what we're going to have to notice is that you got to figure out, once you're given those two numbers, who's the bigger and who's the smaller. So, and that's pretty easy logic. You can just use an if-else. We can also assume that when the method's called, the big one is the first parameter and the second one is values the second, and so we don't have to put in that extra logic. But that's pretty easy. But then we're going to have our code also print out these sentences that I've been doing here also. So once we find out, so first we're going to determine the larger integer. So that's going to be sort of step one here. Then what? We're going to print out that the big is equal to small times something plus the remainder something here. So this, remember, is always the integer division of big divided by small, and the remainder is big modulo small. So that will be the printout, and then what are we going to do? So then what happens is the small becomes the new big, and remember that the remainder, or the modulo, you can call it mod if you want, the mod becomes the new small. And you're going to just repeat this process, basically. You're going to keep going and print it out so it kind of looks cool and you can tell how many steps it took. If you want, you can put a counter in there to count how many steps it took. So you're going to repeat the process until the remainder is equal to 0. And at that point, the current small is the GCD. So you stop and you can print that out if you like. But we're going to have our method just return the GCD, and then you can have main print out that final result for yourself. So what would the actual code look like in Java? So let's take a look here. The header, public static, and it's not going to be void. We're going to return an int. And I think we said call it get GCD faster. And we're going to have two parameters here. And I'm going to assume that the first one in the first position is the bigger of the two. So I don't have to put in extra logic there. It's up to you. But inside this method, we're going to have a local variable, which we'll call mod. And we're going to start right away of assigning it whatever the remainder is when you divide big by small, so immediately. And then we're going to print this out immediately before we start a loop. We're going to use a while loop, okay? And why are we going to use a while loop? Because we don't know how many times it's going to take this repeat process, and a for loop is usually superior when you know in advance how many repetitions there are, and we don't, so a while loop is good. So we're going to do a system.out.println big concatenator, and then we're going to have an equal sign with spaces on either side of it, concatenator, small concatenator, and then we want it to look pretty. We'll have an asterisk. If you want, you could put a space on either side of the asterisk so it looks kind of nice. And then concatenator, and then what's going to go here, it's going to be the big divided by small value. That's the quotient. And then we're going to have another concatenator. Then we're going to have a plus sign with spaces on each side. And then the final value, we got to put a concatenator here again, will be the mod, that remainder. So this is just going to print out the sentence. It'll look real sweet when you run it. Now we begin the while loop. So while the mod, the remainder, is not equal to 0, keep repeating this process. So what is the process? Well, the new big will be whatever the small was, and the new small will be that modulo. And then after you do that, you have to recalculate your modulo. So the new mod is going to be this new big mod the new small. And then you can just do a cut and paste of the println statement we had here, so that will also print out while you're inside the while loop. So if you don't mind, I'm just going to say copy and paste that system.out.println, since it's going to take me too long to rewrite that whole thing again. Okay. And then you're done with the while loop. And of course, we're in the middle of a method. You better have a return statement. So once the modulo, or the remainder, is 0, what do we return? Remember, we return whoever was the last small. And so that is the end of this code here. And so, of course, you're going to have to do an ending curly brace because that's required. And so I just want to say thanks for watching. I hope that you were able to understand this wonderful, powerful algorithm called Euclidean algorithm. Happy programming.